this is Gina Piscatelli with a lecture on chemistry for students in Anatomy and Physiology 1 at Madison Area Technical College. In this general chemistry review, we'll talk about 4 topics. Part 1 will be what are elements and a little bit about the periodic table. And in Part 2, we'll look at the structure of atoms. In Part 3, we'll define what an isotope is. And in Part 4, we'll discuss how ions are formed. So the reason that we talk about chemistry at all is because it's important to how our body functions. Things like how the blood carries oxygen to the various molecules that are involved in muscle contraction. All physiological processes, indeed, depend on how atoms and molecules interact. There is a specialized field in chemistry or in biology called biochemistry, and that focuses on the behavior of the elements that are commonly found in our bodies. So to start with Part 1, the elements, what's an element, and how are they presented in the periodic table. Let's look at the periodic table together. It's a layout of the 92 naturally occurring elements that make up all matter. These elements are arranged according to their properties in the periodic table. Things like how many protons do they have, how many electrons, and each vertical column is a group, and groups are numbered 1 through 8, usually using Roman numerals. I know this is too small for you to see. You'll always be given a bigger picture when you need it, but we're going to only discuss a few of these elements in our class. In fact, as noted on this slide, there are 4 major elements that make up about 96% of the human body. These major elements are oxygen, carbon, hydrogen, and nitrogen. We are considered carbon-based organisms, but if you look at the percentage, really we are made up of 65% oxygen. That's a lot. There are lesser elements in the body as well that make up the rest 4%, and then there are trace elements that we have very little of, but they're important as well. Things like zinc, for example. Our DNA needs zinc to function, but the quantity is so low that it's called a trace element. Some of the other lesser elements that will be important later in the semester when we do organ systems are calcium, chlorine, iodine, iron, phosphorus, potassium, and sodium. Some of those we'll talk about in A&P 1, others in A&P 2. So an element is a fundamental irreducible substance, and that's what's listed in the periodic table. An example would be the element carbon. An atom is the smallest structure or particle of an element that retains all those properties that the original element has. An atom has no charge, and therefore it's considered neutral. So the smallest component of carbon would be a carbon atom. So now we're going to look at the structure of an atom. This is a generalized structure for all different elements, atoms. Okay, so there's 2 major regions. The nucleus, which is in the center, right here, and then orbitals, which are drawn circling or orbiting the nucleus. An atom has 3 particles called subatomic particles: protons, neutrons, and electrons. Both protons and neutrons are located in the nucleus, and they give an atom its mass, or weight, if you like. Electrons are orbiting the nucleus. So they're located in different energy levels that we call orbitals. Sometimes people call them shells. So just to review these properties of subatomic particles, they all weigh the same in terms of mass. They all have been designated as having one atomic mass unit. Charge varies though. Protons are positively charged. Again, remember, they are in the nucleus. Neutrons have no charge. They're neutral. And then electrons are negatively charged. And of course, opposite charges are attracted to one another. So the negatively charged electrons are attracted to the positively charged nucleus. Orbitals are numbered from the nucleus and then towards the periphery. So the first orbital would be here, and then this would be the second orbital, this would be the third orbital, and this would be the fourth orbital. The orbital that's closest to the nucleus, orbital number 1, can only hold 2 electrons. And you can see that there are 2 right here. Here's one, and here's the other. All the other orbitals can hold a maximum of 8 electrons. 8 electrons. That doesn't mean that every atom has that many electrons, but that's the maximum that orbital, that distance from a nucleus, could hold. The last orbital that has at least 1 electron in it is called the valence orbital. And this is really important because the electrons that we consider in that orbital, they're called valence electrons, really dictate the chemical behavior of an atom and how it interacts with other atoms. So just to review atomic structure, we have an atom here which has 10 protons and 10 neutrons. Because there are also 10 electrons, this particular atom is completely neutral and all the orbitals are full. In the periodic table, elements are arranged according to the number of protons that an atom has. The number of protons is called the atomic number, and it's usually located in the upper left of that element's entry in the periodic table. For example, the entry for oxygen, its atomic symbol is O, shows an atomic number of 8 right there. This means that oxygen atoms have 8 protons. Now, because atoms are electrically neutral, it's what an atom is, it's always neutral. It will have equal numbers of positive charges and equal to negative charges. So if oxygen has 8 protons, it also has 8 electrons. All oxygen atoms have 8 protons and 8 electrons. Also in the periodic table entry, you'll notice there's another number beneath the atomic symbol called the atomic mass. And the atomic mass is the mass of an atom's nucleus. So in the nucleus you have both protons and neutrons. Now the weight is always 1 atomic mass unit. So from this entry of 16 for oxygen, you can subtract 8 protons, and then you have 8 left, so that tells you how many neutrons are present. So there will be 8 neutrons in every atom of oxygen. As I mentioned previously, the number of valence electrons will largely determine an atom's interactions with other atoms. So we need to think about how many electrons there are and how to represent where they are located. So if I go back to the entry for oxygen, we know that there are 8 protons for oxygen and 8 neutrons. We also know that there are 8 electrons. And the reason we know there's 8 electrons is because there are always equal numbers of positive charges to negative charges. So there's always going to, if there's 8 protons or 8 positive charges, there's always 8 negative charges. And we'll do more examples in a little bit. So because atoms tend to establish full valence orbitals, meaning they want to have all the orbitals full, the number that are present in an atom's valence shell determines how it's going to react with other atoms. This tendency to want to fill its valence orbital is called the octet rule. To fill its orbital, an atom could share, gain, or lose electrons. And another thing that plays a role in the reactivity of an atom is that electrons prefer not to be solitary. They like to be paired. So we're going to look at where these electrons are located by drawing some Lewis dot structures. So what a Lewis dot structure is a drawing that simplifies an atom and includes the atomic symbol plus just the valence electrons. And that's really helpful because, of course, as I've mentioned a number of times already, how an atom interacts with other atoms depends on the number of valence electrons it has, generally. So we're going to look at an example here. Second. With carbon. So carbon, if you look at the entry for carbon, it has an atomic number of 6. That tells us 6 protons, and because protons and electron numbers equal each other, carbon has 6 electrons. It also has an atomic mass of 12, so you could determine how many neutrons exist. That would be 6 as well. So when we draw these simplified atoms, we first put the chemical symbol in the center. And then we draw orbitals with electrons in them. Since we know that carbon has 6 electrons, the first orbital has 2, 1, 2, because that's the maximum it can hold. And the second orbital has 4. So there's 4 electrons. Now how many more can fit in this valence orbital would be 4. So 4 more could fit. That tells you, just glancing at this, tells you right away that it's probably going to want to gain 4 other electrons in some manner. And we'll talk about that later. So a Lewis dot structure, the most simplified, even beyond what I've just talked about, only shows the valence electrons. So this is a Lewis dot structure for carbon. You just put the 4 valence electrons around the atomic symbol. So using this octet rule and these Lewis dot structures, we can predict the reactivity of an atom. So for carbon, 4 more electrons would fit into that valence orbital. So I'm going to predict that it will gain 4 electrons from neighboring atoms to make that valence orbital stable. And I'll show you an example of how it does that. Let's look at a different example. Hydrogen. Hydrogen has an atomic mass of 1. So it has 1 proton, and therefore it has 1 electron. It doesn't have any neutrons, 0 neutrons. I better make that kind of like this, 0 neutrons. But remember, so it's got 1 electron, and 1 electron is in that first orbital. Electrons don't like to be alone, so 1 more will fit in this first one, and I predict that it's going to want to gain 1 because they don't like to be paired, or they don't like to be alone. So my prediction is a neighboring atom somehow will donate its electron, or the hydrogen could lose this one too. That would equal chances of losing 1 or gaining 1. So let's look at some examples with carbon, or an example with carbon. So we had originally the Lewis dot structure of carbon right here. It was like this. And we also had hydrogen. Notice that carbon, if it has some neighboring hydrogens, can bond to 4 different hydrogen atoms, because then it will have 8 total electrons in that valence orbital. 4 from the hydrogens and the 4 that it originally had. This is the structure of methane. And methane is an organic compound because it's composed mainly of carbon and hydrogen. And the carbon is bound to 4 different hydrogens. So that's kind of how you draw Lewis dot structures and how you determine how many electrons are in the valence orbital. We will talk about bonding again in the next lecture. So the next part that I'd like to review from your general chemistry class deals with different forms of atoms called isotopes. So for some elements, not all elements, but carbon, it's true, there are different forms of atoms, and these different forms, as I mentioned, are called isotopes. They vary in their mass, and that mass varies because different forms of carbon will have different numbers of neutrons. Sometimes this also changes their physical properties, such as the rate of decay, but their chemical property will be the same. So all isotopes of carbon have the same chemical reactivity or bonding with other atoms. So I'm going to show you examples of these carbon isotopes next. So there are 3 carbon isotopes that are known to exist in nature, or commonly anyway. Carbon 12 is one type of atom, carbon 13 is a different, and carbon 14 is another type of carbon atom. All of these are actually called isotopes because they all behave similarly chemically. They all have 6 electrons. They all have 6 protons. Whoops, I can't draw there. 6 protons, they all do. There, and there. But what varies is their nucleus due to the non-charged subatomic particles called neutrons. So carbon 12 has 6 neutrons, carbon 13 has 7, and carbon 14 has 8. That's what an isotope is. Just a different form of an atom. Now, when you look at the periodic table, you'll notice that the atomic mass is not usually a whole number. And that's because these different isotopes are taken into account when they calculate the atomic mass. So the prevalence or frequency of carbon 12, 13, and 14, it's all averaged together to come up with the atomic mass. So the atomic mass is a little over 12 on average. Now the reason we talk about isotopes at all in human anatomy and physiology is because There are some medical uses for these isotopes. For example, MRI, magnetic resonance imaging, as well as some contrast dyes that are used in different imaging techniques, detect isotopes that are part of water molecules in our body. So we have water, which contains oxygen and hydrogen in our body, but the hydrogens can be of different forms. So we can have the normal hydrogen that we usually talk about that has one electron and one proton but no neutrons. Or there's a hydrogen isotope called deuterium or hydrogen 2, which does have a neutron, so it's a little heavier. And then tritium also has 2 neutrons, so it's even heavier. There are also certain isotopes that are radioactive and they decay at certain rates. So PET scans, positron emission tomography scans, detect various isotopes. And also sometimes we use the isotope iodine 123 to detect thyroid cancer. So you give a patient this iodine, and the iodine gets put into thyroid hormone. Just naturally, the thyroid gland takes up the iodine, and it's in the thyroid hormone, and that can be detected with different pieces of equipment. So that's why we talk about isotopes at all. So in summary, we've talked about 3 different things. We've talked about what is an element, a fundamental substance that composes matter. We've also talked about an atom. An atom is the smallest particle that has all the properties of an element. And we talked about its structure, how there's a nucleus, and there are orbitals and 3 subatomic particles. And then lastly, we talked about isotopes, how they are atoms, but they're of the same element, yet they differ structurally just due to the presence of different numbers of neutrons. So the last thing that we should review about general chemistry relates to how ions are formed. And what is an ion? An ion is a charged atom. Okay, so it's a charge, it's not even called an atom. Because when we use the word atom, we mean a neutral particle of an element. Okay, a charged form of an atom is an ion. So an ion is always charged. It's either positive or negative, and an atom is always neutral. Now the charge comes about in an ion because the number of protons does not equal the number of electrons. So we're going to look at some examples of that. There are 2 types then of charged particles or ions. Cations are positively charged and anions are negatively charged. So a cation, since it's positively charged, will have more protons than it does electrons. An anion, because it's negatively charged, will have more electrons than protons. So I'll just give you an example of a common cation that we will see in this class, and that's sodium ions. Sodium has a positive charge. A common negatively charged, there's 2 of them that we'll come across. A chloride ion is an anion or negatively charged, and then later one that's going to become really important is something called bicarbonate ion, HCO3. That is also a negatively charged ion or an anion. But notice that it's not just one element. It happens to be more of a molecule or a compound. But we still call it an ion because it's a charged particle. So how are these ions formed? Well, an atom is going to have to gain or lose an electron because we start with a neutral atom with equal numbers of protons and electrons, then the electrons either leave or maybe the atom gains some electrons. When an atom loses electrons, we call that oxidation. When an atom gains electrons, we call that reduction. Now that's like something to memorize, right? You're like, oh, I can't remember which one's oxidation and which one's reduction. I tend to remember reduction. An atom is reduced even though it gains electrons. Electrons make it reduced. I don't know how. But there's different ways to remember it, little tricks. One way is using the moniker oil rig. So when an atom is oxidized, if it loses electrons, oil, O-I-E, or O-I-L, I guess, loses. And an atom is reduced if it gains electrons, and that's the rig part. That's not the one I use. The one which is obvious because I made a mistake in there, but the one I use is Leo goes grrr, like a lion, growling. So I just remember Leo, truthfully. When an atom loses an electron, it's oxidized. Leo. Lose electron, oxidized. That's the one I remember. Or gains electrons, reduced. Here's a picture of oxidation and reduction happening. So we're going to start off with a neutral sodium atom here. And sodium has an atomic number of 11. It has 11 protons. So that means it also has 11 electrons. That would leave just a single electron out here in the valence shell all by itself. It's more efficient energy-wise to lose that than to gain 7 to make this orbital stable. So sodium tends to lose this valence electron. When it does so, it becomes an ion because now it doesn't have equal numbers of electrons and protons. There's still 11 protons, but there's only 10 electrons. So this sodium ion is a cation because it's lost a negative charge and it has become positive. Reduction is the opposite. Reduction forms an anion, an electron is gained, and the example I'll show you is when a neutral chlorine atom gains an electron and becomes an anion. So chlorine atoms have 17 protons. We know that from the periodic table. Therefore, also a chlorine atom has 17 electrons. That puts 7 in the outer orbital, meaning there's room for one more to make that valence orbital completely stable due to the octet rule, holding 8. So an electron is gained. Now this is a stable structure. The valence orbital is stable, and we call it an anion because there are more electrons than there are protons, meaning there's more negative charges than there are positive charges. Another ion that we will see quite often are hydrogen ions. Hydrogen atoms are interesting because the typical hydrogen, okay, because they have an atomic mass of 1 and an atomic number of 1. That means there's 1 proton and no neutrons. Because there's 1 proton, there's always 1 electron, because it's always electrically neutral. Often, hydrogen ionizes and loses that electron, and it becomes what we call a cation, and we signify it with an H+, because now it has a positive charge but no negative charge. Because the only subatomic particle that is left in a hydrogen ion is this original proton, it never even had a neutron, and it lost the electron, hydrogen ions are often called protons. So I wanted you just to be aware of the fact that a proton pump, if you've ever heard of a proton pump or a proton pump inhibitor, what's actually being inhibited are hydrogen ions. That's what a proton is in our bodies. It also can be obviously the subatomic particle, but that's all the hydrogen's made up of. Okay, so that's it for general chemistry review. The next topic will be chemical bonding. Thank you.